Okay, so this next lesson is about the electromagnetic spectrum. And I wanted to start out by having you look at this photo, which is of the remnant of a supernova explosion, and this happens to be the Crab Nebula. And what you see there is a color-enhanced image showing some different types of radiation that's being emitted by this Crab Nebula. And of course, this is exactly what we're going to be talking about with the electromagnetic spectrum. It has to do with all these different types of radiation. So we talked earlier in the year about heat and thermal energy, and one way that heat moves is through radiation, I had taught you, and this is exactly what we're talking about. Different forms of radiation, heat moving being one type, and I'll tell you what type it is when we get to it. But it's kind of exciting because these different types of radiation are being emitted by stars of all kinds. For these notes, I would like for you to, first of all, you're writing on page 23, and I'd like for you to set up your notes like a big chart, okay? My advice is to turn the page sideways so that the top of the page is actually over here, and the bottom is over here, so you're writing on it sideways, so you have space. And these are the various types of electromagnetic waves that we're going to be talking about, the various types of radiation. There are 1, 2, 3, 4, 5, 6, 7 of them. So you're going to make 7 spaces to write, and you're going to be writing sideways. I told you to skip down a few lines so that you have room at the top up here to write some things before we begin filling in the chart. So go ahead and set this up on page 23. You're going to have it sideways on the page, and you need these 7 spaces, and you can title them as well so that you're prepared to write when the time comes. And then don't forget to leave yourself room, a narrow column on the far left-hand side of the page for your questions and your headings, and then leave room for a summary also. As we go along, you're going to go ahead and fill in information about each of these different types of electromagnetic radiation. So my goal for you today is, I have 3 of them. First of all, you need to understand that sunlight or radiation coming from stars, okay, this also is anything coming from stars, is called electromagnetic radiation. That electromagnetic waves can differ. They differ by wavelength and frequency, and of course those two are related. And also, what I want you to understand is that white light that we get from the sun is actually made up of different colors of light, and we'll talk more about that later. Okay, let's start by talking about exactly what is an electromagnetic wave, and this can go at the top of your notes. Unlike sound waves, they don't need a medium. So we've been talking about sound waves and how they are carried from particle to particle. It's a longitudinal wave. Electromagnetic waves are not longitudinal. They can pass through empty space. They don't need particles. I guess you could call them a transverse wave, but they're moving without particles. It's just energy moving, which is bizarre to think about, but that's how they work. They're carried by electric and magnetic energy alternating. As I said, they're transverse, and they're emitted by all stars. They all travel at the same speed, and that's the speed of light. It's 300,000 kilometers per second, which is as fast as we think anything could possibly go. And, some people say we can't even really go that fast. Matter can't go that fast. Here's a thought. You ever think about, sound waves and light waves or electromagnetic waves, and how come we can get electromagnetic waves from the sun, but we don't ever hear anything from the sun? Think about that particular question, and maybe we'll talk about it in class. All right, so here is the big chart that I had you write in. We're not filling anything in just yet, but you might want to mark on one end, on the radio and TV end of your big chart, you might want to write down that they have low frequency waves, the wavelength is long, and they have low energy. Okay, so remember, wavelength and frequency are related. Longer wavelengths mean lower frequencies, just like with sound waves. So our radio and TV waves, this is the lowest end. And then on the other end, write down that they are high frequency waves. They have a short wavelength and very high energy. And this is our gamma ray end. Okay, so go ahead and add this information and this information on either end of your chart. Okay, so here's another version of the whole electromagnetic spectrum. The electromagnetic spectrum includes all of those different waves that I had you write down: radio and TV waves, microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. And this chart is a real simple way of thinking about it. At the top here we have the wavelength in meters, and you can see radio waves are quite large, 10 to the third power, which of course is, what is that? 1,000 meters. So some radio waves, their wavelength is as much as 1,000 meters, and so here this is depicted as a longer wavelength here. And then they get smaller and smaller and smaller wavelengths as you go along, and you can see here gamma rays are quite small. That's, I think, a billionth. I could be wrong, but I think that's a billionth of a meter. Really small. And then here you have some suggestions as to what kinds of things are the same size as these different waves. So radio waves are as big as buildings. When you get closer to microwaves, they're about as big as people. And then you have the size of an ant, which is somewhere between microwaves and infrared. And then visible light waves are actually a wavelength of about the size of a bacteria, which is smaller than the cells of your body. Bacteria are tiny by comparison. And then when you get down to things like ultraviolet and X-rays, they're the size of molecules or atoms. And then gamma rays are really small. They're the size of the nucleus of an atom, and you know that that's very, very small. And then at the bottom of your chart, you can see that the frequency goes the other way around. They're smaller on this end and much bigger on this end. So the frequency, the number of waves that pass per second, 10 to the 20th power for gamma rays, and 10 to the 4th power for radio and TV waves. All right, so now that you know a little bit about their wavelengths and frequencies, I want to go through each different type of electromagnetic wave, all 7 types, and give you just a little bit of information that you can fill in your chart. First of all, radio and TV waves. Okay, radio and TV waves have the longest wavelengths. They can pass through buildings because they can pass over buildings, but some of them are small enough they can pass through buildings. They have the lowest amount of energy, and because of that, they never hurt us. They're not in any way harmful. And of course, we use radio and TV waves for communication purposes. I thought it was interesting to tell you exactly the difference between AM and FM radio. You probably have heard of those things, and you probably spend most of your time listening to FM radio, but there is also AM radio. And the AM stands for amplitude modulation, which means the signal is carried by changing the amplitude. And if you look at this wave right here, you can see that it's got a big amplitude here and a smaller amplitude here, and that's actually what's carrying the signal. FM stands for frequency modulation, and in this wave, you can see what's changing is not the amplitude. The amplitude stays the same, but look what's happening. You have a high frequency here and a lower frequency there. And so that's the difference between AM and FM radio. It's the way that the radio signal is actually carried. All right, the next shorter wavelength waves of the electromagnetic spectrum and higher frequency are actually microwaves. And we all are familiar with microwave ovens that cook food through using these microwaves. But we use microwaves also for cell phone communication, satellite communication, and also GPS. We use them in ovens to heat our food, and the way that the oven works is that these waves are readily absorbed by water, fats, and sugars. And so by emitting the waves inside the oven, they're actually, that energy is being absorbed by these things that are in the foods, and then it heats them up. They are not absorbed, or they're less able to be absorbed by things like plastic and glass and ceramic, and so the food gets very hot, the dish doesn't get as hot. It will still heat up a little, and of course the food itself by conduction is heating up the bowl or the plate, but mostly what's happening is that the food's getting heated up. The other thing about microwaves is that they're reflected by metal, and so if you put metal in a microwave, in most microwaves, the energy is amplified, and of course you've probably heard of things that go wrong in microwave ovens when you put metal in there. It generates way too much energy and things can catch fire and things like that. You could break your oven, so you don't want to be doing that. All right, the next shorter wavelength electromagnetic waves and higher energy and higher frequency are infrared. Now, when we talked before about heat being transmitted by radiation, this is really what we're talking about, is infrared waves. This is heat lamps in restaurants, if you've ever seen a heat lamp keeping food warm in a restaurant. Infrared cameras also. This is how our TV remote controls work, is by infrared. And we use infrared to locate survivors after natural disasters, after an earthquake or a hurricane, where people are underneath rubble. They can find them because of the warmth of their body, the heat being generated by their body, the radiation's being given off, and we can use that to locate them. One of the cool things is that snakes, pit vipers, they can actually detect infrared. That's how they find their food. The picture down at the bottom is, this first photo is taken with regular visible light, and you can see he's just standing outside. There's snow on the ground and ice on the ground, so you can tell it's cold out. But he's just standing there waving. And then this picture is the same gentleman taken through an infrared camera instead. And what's cool is you can see that his surrounding area is around about 30 degrees Fahrenheit, so it's cold out. But you can also see his face is giving off a lot of warmth. It's above 65, which isn't surprising. It's probably close to 98.6. And then you can also see areas where he's giving off a little bit of heat. You can see his coat is not giving off very much heat at all. It's a good insulator, but his pants, it looks like he's just wearing ordinary pants, so they're giving off some of the heat, and it looks like his gloves don't work that well either. But this is infrared waves being given off of his body. Aw, baby pig. Okay, right in the middle of the electromagnetic spectrum is a range of wavelengths and frequencies that we can see. It's very narrow range. You might want to look in your book or something where, well, actually I might have a diagram, but it's a very tiny portion of the electromagnetic spectrum. So all this radiation that's coming from the sun, only a tiny narrow bit is what we can actually see. We use visible light, of course, obviously, to make our way in the world, but also it's used in CDs and DVD players. That's how they work. And, of course, lasers. And the thing that I said at the beginning of this lesson, of course, is that white light is actually a combination of all the colors. Now, one of the things that we're going to be doing in class is using something called a prism, which is pictured here. And a prism is works by separating out the colors that we find in white light. So that's what this little diagram is. White light coming in, and then coming out are all the colors of the rainbow. And then, of course, we've seen rainbows in the sky, lots of them around Florida. And basically the rainbow works by the water droplets in the sky doing the exact same thing that prism is doing. And so it's the white light that we ordinarily see coming from the sun simply being separated out into its various colors in the sky right before our eyes. All right, here's a diagram of the white light spectrum. In other words, all of these colors can be found in white light, and they range in wavelength, and these are nanometers, so they're a billionth of a meter, really small, but starting with the longest wavelength ones, about 700 nanometers, and the shortest wavelength ones, about 400 nanometers. Anything beyond 700 and 400 we can't see. That's just beyond our ability to see, but the colors that we see in the rainbow, or the colors that make up white light, the 700 nanometer is what we would call red, 400 what we would call purple or violet, and then everything in between. Roy G. Biv is an acronym telling us the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. All right, just beyond the visible range is what we call ultraviolet light, and you've probably heard of it, UV. We always call it UV around here, and it is high energy waves, and we use it, of course, to tan our skin, which isn't necessarily healthy, and also it kills bacteria. It is damaging to our eyes. That's why we need to wear sunglasses. It's damaging to your body cells, and it can cause skin cancer, along with, of course, suntan and sunburn. But those are all just ranges of harmfulness. There's no such thing as a healthy tan, because even tanning your skin is potentially harmful. So you got to watch out for those UV rays. Whenever you hear about or see something in black light, it's actually fluorescence of ultraviolet light, and so we can talk about that more in class as well. And also some organisms can see in the ultraviolet, and I think that's kind of cool. For instance, bees, when they look at a flower, they don't see what we see. They see something different. They would see that same flower this way if they were looking at it, and I think it's kind of cool because it almost looks like there's a bullseye pointing right to where the nectar is, which is, of course, what they're interested in. Right, here's another diagram giving you an idea of where these wavelengths are with respect to the other types of radiation. So here between 700 and 400, like I said before, is our visible range. So these wavelengths in here are what we can see. Just longer wavelengths than that are the infrared, which we already talked about. And then just shorter from that, down to about 100 nanometer wavelength, are our ultraviolet waves, and there are three kinds. There's the UVA, the UVB, and the UVC. Okay, just beyond the ultraviolet are the X-rays, which have very high energy. They can pass through skin and muscle. And the thing about X-rays is that they can be very damaging to your cells, just like UV. The higher energy you get, the higher frequency you get, the more damage you're really going to get. But we can use X-rays to take a picture of inside the body because they can pass through skin and muscle, but they can't pass through bone. So you get to see the bone. You can see here, this is kind of a cool picture of a fractured leg bone, it looks like. Tibia and fibula both. But because they're damaging, this is why we wear a lead shield. Like if you go to the dentist and they're taking X-rays of your mouth, they have you wear that apron made of lead. It's real heavy because it blocks the X-rays, and you don't want the X-rays to go anywhere you don't need them to go because they can be damaging to your cells. And then, of course, they're used in airport security. If you've ever been recently to the airport, you know that you have to walk through those X-rays. All right, last but not least, and thank you for putting up with this long podcast, the highest energy and shortest wavelength electromagnetic rays are the gamma rays. These are very damaging. They can be blocked by concrete or lead, but nothing else will block them. We do use gamma rays on our fruits and vegetables sometimes because they kill bacteria, and you've ever heard of irradiated food? That's what it's talking about. They just pass the food through some gamma rays to kill the bacteria on there. We also use them in medicine to treat cancer. If you've heard of people getting radiation treatment, that's what it's talking about. And it's also used to sterilize medical equipment because it kills the bacteria. But it is instantly damaging to our body tissues. It's not something you would want to be exposed to. Luckily for us, even though they come from the sun, our atmosphere blocks all of the gamma rays, or they would be potentially harmful to us as well. All right, so thanks again for putting up with this really long podcast, but I am going to offer you some extra credit. And for those of you who actually are watching the podcast and not copying notes from someone else, because I know some of you are doing that, of course, probably not you because you're listening to the podcast, but if you listen to the very, very bitter end of this thing, here's what I want you to do. On page 23 on your notes, in the top right-hand corner of the page, write the date, and then below the date, in the top right-hand corner, draw a sun. Make it cute, color it in yellow, and I'll give you extra credit when I check your notes on Wednesday. Okay, have a great weekend if you're listening on Saturday, and have a great week if you're not. See you at school.
Made with Doodlecast Pro.